Okay, I think we have just started the recording. And so, hello and welcome everyone. Today we have Ajay from IISc, who is a PhD student working with Orko Basu. And he will be talking about his upcoming micro work on GPU and over synchronization. So, over to Ajay.
Yeah, yeah. Thanks for the intro, Biswa. Hi, everyone. So I'll be talking about my upcoming work over synchronization in GPU programs. So let's get started. So a large swath of today's software relies on GPUs for its execution. The applications range from image processing, graph processing, DNN training, and you name it, right? And GPUs are an expensive resource as well. And for the sake of all these applications, it's important that GPU should be utilized in the best possible way. However, it's not that easy for GPU to be utilized in the best possible way, and there are lots of factors that comes or becomes obstacles. Right? One of the things is these software interactions that are brought about by new features that these GPU manufacturers keep introducing. For example, scoped operations, and we'll be talking about this in detail in this part of the talk. Next is that manufacturers expect the developers to manually make modifications to their program to make the program a bit better. And this manual modification could be error prone or can lead to inefficient design choices, which can still lead to GPU being underutilized. And finally, a lot of GPU debugging softwares are not up to the mark. For example, NVIDIA Insight is a well-known profiling tool for CUDA programs. However, it will tell the developer then what are the reasons why the programming is slowing down, but it doesn't necessarily provide exact modifications that the programmer must do so that they can improve their program performance. As due to these factors, a lot of these new features end up getting not being used by the developers, and that leads to poor performance of the program. In this talk, I will be focusing primarily on scoped operations. There are other features as well that are getting that can get not being used by the developers, but we'll be focusing on scoped operations. This is a brief outline of the talk. First, I'll be talking about the background, where I will be primarily focusing on scoped operations. Then I'll be talking about complexity of scopes. I'll be spending majority of my time in this section where I'll be giving lots of code examples and try to help you understand why this is an interesting space of work. Next, I'll be talking about scope advice, primarily the design philosophy that we chose in order to implement scope advice and the challenges that we found while building scope advice. Then we'll jump to the evaluation where I talk about the effectiveness of scope advice and the performance improvements that we get from on the program when we eliminate these over synchronizations. And finally, some numbers about overheads of scope advice. With every new generation, a common trend that we are looking at with GPUs, albeit from manufacturers of NVIDIA or AMD, is that the number of concurrent threads are constantly increasing. Right? For example, over here, you can see that NVIDIA, the number of concurrent threads are increasing with every newer generation, which makes global synchronization very complicated and difficult. As such, the synchronization model that is necessary for these GPUs also has to scale with the increasing size of the GPUs as well as the number of concurrent threads. Manufacturers such as NVIDIA have came up with a solution called scope synchronization in order to provide scalable synchronization on GPUs. The scope qualifier on synchronization operations tells the subset of threads that should be synchronized when you perform subset of threads that has to be synchronized when you perform synchronization. WOPs are the smallest set of scheduling unit on a GPU that is generally a set of 32 threads. A thread block is generally a set of WOPs that are always scheduled on the same multiprocessor, and a lot of thread blocks together form the grid. Kernels are launched on the GPU at the granularity of grid. And in order to synchronize between these threads, you can use different scopes such as block scope and device scope. The scopes that are generally used to synchronize between two threads depends on where these threads are present on the GPU. As an example, if you look at here, two threads which are on different thread blocks, if they want to synchronize with each other, they need to use device scope operations because they can be running on different multiprocessors. In CUDA, the way how the scoped operations are exposed to the programmers are using fences and atomic operations. The same set of operations are also exposed in OpenCL, which is the AMD software stack, but we'll be primarily focusing on CUDA terminology in this talk. So as you can see, the same scopes, for example, block scope, device scope, which is the default scope in case of CUDA, and the system scope are present in both fences and atomic instructions. And the key takeaway from this slide is that the programmer is expected to use the exact scope of operations at any point in time based on what they require. To understand the scope operation better, let's take a look at the way how these scope operations interact with the hardware structures. The fence operations need to ensure two things. One, in case of block scope, they need to prevent reordering among the memory operations. Two, they need to ensure that the data is written to or read from the L1 cache in the multiprocessor which is present on the GPU. Similarly, the atomic operations which are block scope need to ensure that the visibility, that is the effect of the atomic operation, has to be present in the L1 cache or below. Similarly, the device scope operations needs to ensure synchronization across multiprocessors. So they need to find a common ground between these multiprocessors, which is the L2 cache in this case. So the fence operation, which is device scope, still needs to prevent reordering of memory operations, but now it has to ensure that data is written to or read from the L2 cache. Similarly, the atomic operations have to ensure visibility of its execution in L2 cache or below. Due to this additional task that the device scope operation needs to do, a block scope fence is 21 times faster than the device scope fence because the block scope fence has to only limit itself to the L1 cache, whereas the device scope has to bring data to the L2 cache. This comes to the next point that using a wider scope than needed can actually degrade the performance of your program. This raises a natural question as to when exactly is the device scope fence actually necessary. So let's take an example over here where there is a global array that is using global memory and it is accessed across different thread blocks. So these thread blocks are actually executing on different multiprocessors. The fence, which is a device scope fence in this case, which is present after the write to this global memory, flushes the L1 cache and ensures that the data is written to the L2 cache. Similarly, the fence before a read to the global index ensures that the L1 cache is invalidated and anything that is read by the thread after the fence is from the fresh data from the L2 cache. At this point of time, because of all these complicated structures that the scopes bring, it's always hard for the programmers because the programmers themselves has to choose which synchronization operations they have to use. Based on the previous example, it seems fairly obvious as to when a programmer has to use a device scope fence or not. However, CUDA programming guide provides a lot of features which make the decision a lot more challenging. For example, just to quote a section from the CUDA programming guide, the volatile qualifiers in CUDA can disable caching a value into registers or the L1 cache. So this raises a question, what exactly are the fences operations that has to be used in the presence of volatile memory access themselves? To understand this better, let's take a look at an example where there is a producer thread and a consumer thread, and they are just using the producer consumer data communication pattern to share information. Though this example seems a bit made up, this is actually a simplified snippet from the NVIDIA CUML repository. Over here, the data and flags are declared as volatile, and it follows the same structure as the producer-consumer synchronization pattern. Now, the producer and the consumer are actually scheduled on different simultaneous multiprocessors, and the data initially is resident on the L2 cache. Initially, the producer is writing the data to the L2 cache using the store operation and then a fence. At the same time, the consumer is actually spinning on flag value to see if it has changed. Next, the producer writes the flag. At this point of time, the fence in the producer is necessary to ensure that the write to the data has reached to the L2 cache first before the write to the flag itself. And the consumer is still spinning till it reads the new value from the L2 cache. Once the consumer reads the fresh value from the L2 cache, it then proceeds to read the fresh value of data, at which point of time the consumer reads the value that the producer was supposed to read. However, note that the consumer was using volatile operation. At any point in time, the L1 cache was not involved at all. Thus, the consumer required the fence operation only to prevent the reordering of the flag and data memory operations and nothing else. The additional overhead that the fence gives, that is the flushing of data as well as invalidating the L1 cache, was exactly not necessary. And if everyone can recall, a block scope fence can also provide this kind of guarantee, that is the prevention of reordering of instruction. Just coming back to the example, we can see that the thread fence in the consumer in particular is something that was not necessary. This is the situation that we call as over-synchronization, as in the synchronization was necessary. However, the scope of synchronization that was used was well over the scope that was actually needed. And thus, if you just change this scope to a block scope fence, they still ensure correctness while retaining the same guarantees that the programmer needs. And this is the performance that has to be grabbed by the developer. Another example is in using this code snippet that is taken from CUDP repository, another one of NVIDIA's libraries. This is a busy slide. However, the key takeaway over here is all the communication using the address pad is happening via shared memory. At any point in time, there is no need of device scope synchronizations over here. As such, the fence that is present over here, which is highlighted, is not necessary and it is over-synchronized. Moreover, if you lower this thread fence operation to a block scope operation, that itself is also redundant because sync threads, which is an execution barrier within a thread block, already provides the guarantees that the thread fence block should provide. As such, this fence operation is actually redundant and it can be easily eliminated while retaining the same program guarantee. This comes to the key contributions to our paper, that we are the first to show that programmers often leave performance on the table due to the way how they choose the scope synchronization operations. We show that these sort of performance bugs exist because of over-synchronized operations and redundant synchronization operations. We show 3 different variants of over-synchronization, 2 of them which were showed in the previous examples. And finally, there is an additional example that is due to intra-thread blocks acquire release patterns, and I'll be happy to talk about it later if needed. Eliminating this over-synchronization from the GPU programs gives a performance up to 54%. Hopefully by now, I guess everyone is convinced that finding over-synchronization is non-trivial because of the way how these memory operations as well as synchronization operations interact with the hardware, right? As such, the programmers, there is a need for an automated tool at this point of time. And the key necessity can also be because the programmer, it eases the burden from the programmers. The programmers can initially just focus on the functional correctness of the program, and then they can use this sort of tool to find possibilities of performance improvement. That's where we bring in scope advice, where we build an automated framework to find over-synchronization in CUDA programs. On a high level, scope advice expects a user program and a program input as an input towards the framework. It uses NVBit to instrument the program on the CPU and launch the instrumented program on the GPU. The instrumented program does a lot of things apart where it actually captures a lot of metadata, where where we capture what kind of memory every thread is accessing. We also keep track of all the fence accesses, the memory fence accesses that the thread is actually performing. And at the same time, it is actually sending the trace of the program's execution to the CPU side, which is actually where we keep track of the trace. The trace consists of the address that a thread is accessing, the loads, whether the operation that was performed was a load or a store, the scope of operation, thread identifier. A lot of things are taken into consideration when we capture this trace unit. Once the program terminates, we copy this metadata back to the CPU and we finally perform a lot of analysis on the CPU. We use a lot of rules. Rules can be thought of some similar structures that we discussed when we talked about why or when should a programmer be using device scope fence. However, we add in tunables based on the fact if the memory access was volatile or not. Once we detect this sort of over synchronization, the output to the programmer is the final file name, the line number in the file, and the variant of over synchronization that the developer has to know. At this point in time, the developer knows the exact line that has to change and they can gain performance improvement. There are a lot of unique challenges when we were building scope advice. And the two challenges that we came across was high runtime overheads, where because these are dynamic analysis, there are lots of instrumentation overhead that come into picture. Even though scope advice is an offline debugging tool, it's still not good to wait a long time for an analysis to show a good results. And the second key unique challenge was that analysis itself is input dependent. This is something which is common to all dynamic analysis, and we'll see how we found a way around this challenge. To reduce a lot of runtime overheads, we employed lots of CPU and GPU runtime optimization. A key observation that we did was our algorithm to detect over synchronization is very simple and it can be easily parallelized on the CPU. And we just perform the detection using lots of threads based on the number of threads which are present on the CPU. Similarly, we perform lots of on GPU runtime optimization. For example, if you recall that a lot of trace elements are actually continuously spent between the CPU and the GPU throughout the course of execution. Many times these trace units are not actually contributing towards the necessity of a fence operation. For example, if a data structure is just read only, at that point of time, they will never need fence operations for synchronization. However, a nice implementation will still keep on sending these trace units to this CPU. We enable trace filtering where we selectively send the trace to the CPU. This helps us avoid a lot of cases where the program accesses can be streaming in nature, where the data is read only once or a few times. At that point of time, the trace is just not sent to the CPU for performance analysis. Other overhead that was created by continuously creating the trace was eliminated by sampling the execution of every thread. We notice that every memory access that the thread creates or generates is not necessary to find out which fence operation is actually needed. At that point of time, we selectively process the GPU thread's execution, and it still does not hamper the correctness of our tool. Other challenge that we discussed earlier was that the analysis could be input dependent, right? Though which is this observation or situation comes very rarely. The user, in order to deal with this, we create a wrapper where we take scope advice and we, rather than giving a single input for it to analyze over, we give it multiple inputs where the inputs could be generated by a fuzzer, it could be the testing suite that the developers wrote, or it could be just random set of inputs. In our work, we actually integrated scope advice with a random fuzzer that was already available just to show the programmability. And what we do is we run scope advice across all these inputs. When we aggregate the results, what we try to do over here is we find the intersection of all the results which are generated across all inputs. The common results that are available across all inputs are what the set of fences that the developer finally sees, and that's what is declared as over synchronization by the scope advice. Looking at our evaluation, what we ran our evaluation on an NVIDIA RTX 3090 GPU, and to show the applicability of scope advice, we ran it on a desktop class machine, which is Ryzen 9 on 128 GB RAM, though it was not necessary. And we showed our evaluation on CUDA 11.2 and Ubuntu. In this table, I have listed all the applications that we ran scope advice against, the actual number of over synchronizations that are present on the GPU. This actual count was something that was figured out manually by our analysis. And the ones in the reported column are the ones that scope advice showed. The variant column shows what are the sort of variants that this actually application has. The applications which are marked with star are from NVIDIA library. As you can see, the over synchronization cases which are actually found and with the ones which are actually reported by scope advice do match. Even in situation when there was no over synchronization present, scope advice did not report any in those cases. Moving on to the performance improvement, what we did in case of to evaluate performance improvement was to first have the original set of programs, and we ran over them across multiple inputs, and we ran the same program by eliminating the over synchronization across the same set of inputs. Over here, these applications show up to 54% performance improvement when we eliminated this over synchronization. And this elimination of over synchronization leads to a lot of benefits. For example, a good amount of L1 cache bandwidth can be used. However, the key metric that we want to show over here is a thread fence can be a blocking operation on the GPU because it has to wait till the entire invalidation or the flushing of the cache has to happen before it moves on to the next memory operation. As such, over here, we report the stalls that are present due to fences on these programs. As you can see, originally, there are lots of stalls cycles on an average across the entire program execution, which was easily reduced by removing this sort of over synchronization. One of the applications did not see any performance improvement by elimination of over synchronization. However, it can be associated with the fact that it was never stalled due to fences to begin with. As such, eliminating over synchronization did not benefit at all. Finally, in this slide, I want to show the amount of overheads that scope advice adds. Even though it's a debugging tool, like I said, we still want to minimize the overheads that the developer has to wait to get the results of over synchronization. As you can see over here, we are on a step-by-step level adding an optimization where the naive is the leftmost bar, and then we add parallel CPU analysis, then we do execution sampling, and finally some sort of trace filtering, which just reduces the overhead by a huge margin. Over here as well, one thing that I would like to tell is most of the overheads are because of NVBit framework and not because of our analysis. As such, at any point in time in future, if NVBit itself has reduced its overheads, we'll also see a performance improvement, a reduction in runtime overheads of scope advice. There are a lot of details in the paper where most of the time in our paper was spent on actually validating our optimizations against PTX memory model, where we show that our optimizations are valid even against a PTX memory model, which is actually corrected using lots of solvers. We also discuss a lot about our rules of how we identify over synchronization. We talk about why we chose dynamic analysis and why static analysis will not be helped to find all cases of over synchronization. And finally, we have some evaluation where we show the memory overheads that are present because of scope advice. To summarize, a lot of GPU programming features gets added by these manufacturers, and the manufacturers expect the developers to manually modify their program. to get benefit out of this. However, these features are not easily something that the developers can use because of their complex nature. And in this work, we are the first to identify a new performance bug which is present due to scoped over synchronization. We show that our performance can improve by up to 55% by just modifying 2 to 3 lines on average. And finally, we built scope advice, a tool which is capable of accurately identifying and reporting cases of over synchronization in CUDA programs. Our artifact is available on GitHub, and it's reproducible, and I'd request everyone to take a look and try to use it. Yeah, that's all I had for the talk. I'll be happy to take questions.
Yeah, thanks. Thanks, Ajay. So all these numbers that you have shown, is it dependent on the memory consistency model, or it will be invariant of that?
Dependent on the memory consistency model. So it still follows all the memory consistency model that the PTX provides, right? It still is valid even according to the PTX memory model, even after we give all the optimization.
So what kind of memory model that PTX uses? I don't know
It's a
exactly.
weak memory model. Oh, it's a weak memory model. Yeah.
Lazy one, right?
Yes, yes.
Hello.
Yes.
Any other questions? Yeah, go on.
Yeah. So in Petrik's memory model, as far did any bit able to understand the PTX memory model instructions, because as far as it's only interprets as them as SC instructions.
Sorry, I could not hear. Can you please repeat?
So PTX model. So you run. So your sorry, underlying memory model is PTX model.
Yes.
But was any bit able to report it as a weak memory model, because it generally is any bit able to handle the weak memory model of PTX?
So NVBit is only an instrumentation framework. It doesn't, it just adds instrumentation to the program which is already compiled, and the compiled program is already PTX memory model compliant. So we do not touch the memory consistency model at all in that case. What we discuss in the paper primarily is our optimization are valid even irrespective, means even is valid with respect to the PTX memory model. The NVBit is just a framework to find influence scope device.
It may happen that the fences have different scopes. It can be sequential consistent, or it can be release acquire consistent.
So the fence over here that we are talking about are thread fence, which is at the CUDA programming level, and they are the sequential consistent ones.
Okay.
So the release ones, yeah, what you are talking about are something that is actually available at the PTX level, but they are not straight away exposed to the programmers, and we have not come across lots of programs that actually use those. The most common fence operation that programmers end up using is the thread fence, which is the sequentially consistent.
Okay, so where they're like synchronization between different devices, or you're using only one device?
So we primarily focus on synchronization on the same GPU, so it's only a single device.
Hi, I have a question.
Yes.
I'm slightly new to the GPU stuff, so bear with me. How often do these synchronization fences occur? Is it completely dependent on the programmer and the program that they're working with? Or how often do they need to occur?
So when you say how often, do you mean within a program or across the programming programs that we
Across
actually
the
analyze?
programs.
Okay, across the programs.
Across
Right?
the programs, yeah.
So GPU synchronization is something which is not so heavily used as such, but we are seeing these sort of changes. For example, a lot of these graph applications require this intricate synchronization where every thread has to talk to each other about what they are trying to do. In those applications, for example, in our case, we actually evaluated against UTS, but there are other applications, for example, in Lone Star Bench framework. They actually have lots of graph applications where they use this synchronization primitive. And the other cases where we saw fences are all these frameworks, where there are frameworks like libraries written by NVIDIA or something which are just available in open source. So in general, till some point in time before, most of the applications which are written on GPU are bulk synchronous, where they use this sort of execution barriers. However, this sort of things are changing because of lots of additional features. Like one of the features is independent thread scheduling, where each thread within the warp can start executing independently compared to other threads within the warp. So there is no lockstep always. So this actually brings out more functionality for the programmers to write fine-grained synchronization. So yeah, so right, most of the applications even now are bulk synchronous, but there are a lot of applications or where in open source which are written using this synchronization senses and atomic operation.
Okay, and how many of these bulk synchronizations do you need to perform in the entire scope?
Bulk
I
synchronization.
apologize.
Yeah.
I apologize for the term that I used. So you said you changed the fence from something to
Device
a
scope
thread
to
fence.
block scope. Yes.
Yeah. How many of these fences do you need to perform in the device scope?
Yeah. So over here, let's talk about CUML as we take an example. The number of fences that this application used were 8, and out of those 8, 5 were actually necessary to ensure correctness, and 3 of them were not necessary. So we keep the five of them as device scope and change the remaining 3 into block scope. Does
Okay.
that answer
Okay.
your question? Yeah.
Yeah, that answers it. Thanks.
Yeah.
Hi, I have a question.
Yes.
Hello, am I audible?
Yes, you are audible.
Yeah. So I am just interested in your SGEM. I did not know that you already have talked about this or not. I might have missed that. But in the SGEM, you like your framework has have given one false positive. So can I just know the reason of that? Like why it has given?
Sorry. Yeah. So this SGEM is something which is coming from an cuBLAS source. Right? What happened in this case is, rather than, we cannot term it as false positive because we actually don't know what is actually happening in behind the scenes in cuBLAS, because NVIDIA's cuBLAS is closed source, right? But our tool, because it is dynamic analysis and it can instrument the SAS code, it actually found out that there is a type 2 over synchronization even in SGEM. So we cannot, that's why there is a dash over there, because we actually don't know whether SGEM has that over synchronization or not, but it's actually reported as one by our framework.
Yeah. Okay. I understand. Thanks.
Yeah.
So, Ajay, one more question. So,
Yes.
you have pretty good set of results, but did you still see further scope? Because I think there are still cases or the table that you showed where I guess you still have scope to improve further. Am I right?
Scope to improve further.
So, can you go back to one of the tables where, yeah, hang on, that one. Yes.
This one? Yeah.
Yeah, this one. Yeah.
Yeah.
So, for
So, I
example,
see. Yeah.
yeah.
So I guess you're saying that there is a scope for improvement here because there are still lots of stalls due to fences. I guess
Yep.
that's what you're right. So the argument means the key observation that we wanted to do in our paper was something that the fences themselves are over synchronized. But what our understanding from this numbers suggests that if we want to reduce these stalls, we might have to just rewrite the algorithm altogether so that it changes the program itself. At that point of time, just removing over synchronization won't help much. But my understanding from this is they might have to rewrite the algorithm itself so that the fences or stalls which are present due to fences can get reduced further. It's not due to over synchronization, but in itself, the problem of the algorithm which requires them to use fence. If that algorithm itself could be modified, they can still see lots of
Uh-huh.
performance improvement.
Okay. Okay. Got it. Got it. Yeah. Thanks. Any other questions? Anyone else? Yeah, I guess we are done. And I think because of festive season, the attendance is pretty low today.
Yeah.
But nevertheless, we had a very good talk. And if there are no more questions, then maybe we can stop the recording and, I'll just say thanks to Ajay.
Yeah, thanks. Yeah, means if there are any further questions, please you can write an email to me and I'll be happy to answer. Or you can just raise an issue on the GitHub and I'm happy to respond over there.
Yeah, sounds good. Thanks. So I will stop the recording now. Yep.